So last time we ended up with this amazing diagram, which is essentially showing the map between point configurations, endpoint configurations over the complex numbers or real numbers, and the corresponding maps, the map to the real symmetric matrices that represent the pairwise distances between the points. I have complex C and choose 2 here because one of the two maps, there are two maps which coincide over the reals, as we pointed out. One is the inner product map and the other one is the distance map. So one is shown in orange and the other one is shown in blue. And essentially, they both coincide when the image is real symmetric matrices, but when the they coincide when the domain is complex, is the real numbers, and the image in both cases is the real symmetric matrices, or if you think of it as real distance vectors. And when the point configurations are complex, one of the maps could map potentially to complex distances. And so the matrices have complex entries and potentially complex eigenvalues. And whereas the other map always maps to the real symmetric matrices, except they could have negative eigenvalues. So if we have real point configurations here, the image of the map is always real symmetric positive definite matrices, which means they have non-negative eigenvalues. And if there are complex point configurations, then the inner product map could still maps only to the real symmetric matrices, but could have negative eigenvalues. One thing that I wanted to point out, and I think I did that last time briefly, but it's something to keep in mind when we talk about just having the positive semi-definiteness condition already determining the rank. In those situations, we have to be careful if we're talking about complex or real point configurations. And the example that we had last time was when we had real matrices and they have non-negative eigenvalues, and we want a sort of a path in both the configurations, the configurations domain of point configurations and in the image of distance matrices that slowly moves out of the non-negative eigenvalues to negative eigenvalues. It's forced to either drop rank or increase rank. So in other words, the one of the non-negative eigenvalues will become 0 before it becomes negative, or one of the 0 eigenvalues becomes negative. So in other words, if you're on one of these strata of this cone, real symmetric matrices with non-negative eigenvalues, that cone, in other words, distance, pairwise distances of points in real space, if you're on one of the strata of this cone of dimension strictly less than n-1, so n-2, so let's say, and that means you have points, there's at least, the points don't live in n-1 dimensions, they live in 1 dimension less. So there's one affine dependence. So what you could potentially do is ask yourself, well, I have n-2 non-zero eigenvalues in that case. Remember, the number of eigenvalues is the dimension of the point configuration. And you could say that, well, I want to slowly move out so that I now have one negative eigenvalue. So in other words, the point configuration goes to the complexes. Then if you use the inner product map, you have to either drop rank or increase rank. So drop rank means all one of the eigenvalues vanishes before it becomes negative, or one of the 0 eigenvalues becomes negative. This is not the case if you use the distance map. So in the distance map, you can, you're living in n-2 dimensions, and some new affine dependence happens. And just before the distances, no longer satisfy one of the Cayley-Menger inequalities, let's say, you can still maintain the same rank. And so in other words, the point configuration still lives in the same dimension, and except that now the map is now going to map to, of course, you'll have complex point configuration. And in the case of the inner product map, it will, as I said, map to distance matrix of either one more rank or one less rank. But here, and correspondingly, the point configuration will either drop dimension or increase in dimension. Whereas in the distance map, the point configuration can remain in the same dimension. But if you use, map forward, that quote unquote distance matrix will now have complex entries. So, so that's something to keep in mind when we talk about this idea of when the inequalities, namely the idea, the non-negativity of the eigenvalues, or the Cayley-Menger inequalities, either one of them, when they force the rank, when we say that, we have to be careful which of these two maps we actually use. So that's all I want to say. We'll go deeper into this type of thing later. We're still in the tour stage. So the next topic, which I was already promised last time, was to talk about partial matrices. So we now don't have all the entries of the distance matrix, but only a subset of the entries given. So, and
can I ask a question?
Yeah, sure.
So just on that, just to remember what the map was, we have points P1 through Pn, and for
here, yeah, okay, yeah. Mm-hmm.
For each,
yeah, I think we had it in the previous slide. Yeah. Mm-hmm.
For each Pi, Pj, so each pair of them,
yeah,
we take Pi minus Pj and compute its squared distance or its Hermitian inner product with itself.
Exactly. Those are the two maps.
And that gives us one entry of an n by n matrix whose diagonal consists of zeros.
Exactly.
Okay.
So that's, so you named both the two maps, and the two maps coincide when the point configurations are real. We'll always get positive symmetric, real symmetric matrices that are positive semi-definite. But if the point configurations are complex, in one case, you could even map to complex distances and complex entries in the matrix. And in the other case, you'll still get only the reals, but negative eigenvalues, potentially.
Okay, thanks.
Okay. And what I talked about, the rank is an important distinction. What happens to the rank when you move out of from the positive to the negative eigenvalues? What happens to the rank differs depending on which of the two maps you use. Yeah. Okay. So now let's go to the graphs. So you have matrix. So you have I'm going to go for a second to, maybe I can just use annotation. Let's see. Let's try that. So here we have, so essentially we have a partial matrix. So you have some of the entries given. So let's say I'm going to call the entries that are given, I'm going to mark them like this. These are, of course, zeros. You can always assume that. You're trying to sort of figure out whether you can extend your this partial set of entries. It's a symmetric matrix that's also known, so I'm not going to do anything here. So some entries are given and other entries are not given. So if you look at the ij values, now these, you can think of these are the vertices of a graph. And So essentially this ij entry being present means that the corresponding graph has an edge between I and j. So the given entries represent a graph. And what you want to figure out is whether the remaining entries can be filled up in such a way that I don't know now whether do I now have to save immediately? I probably do. Okay. Okay, so get out of there. Mouse. Okay, and I have to do some kind of clear. There we go. Clear my drawing. Okay. So this, so that obviously didn't, it saved it somewhere. So I think I prefer to use the whiteboard. I'll just use the whiteboard. So if you, the kind of questions you're interested in is whether or not you can extend it to a distance matrix. That means what we mean by that is existence of a real realization. So, positive semi-definite matrix. Whether it can be extended to a matrix of a given rank. So somebody gives you a rank and says, can you extend it to a positive semi-definite matrix of a given rank? And the questions of whether this can be done can again be split into three parts. Does there exist such a completion? How many completions are there? What is the dimension of the completion space, so to speak? And whether it's unique, whether the completion is unique. So these are the three general questions that you're interested in. And it so turns out, as I have pointed out before, if we happen to be on the boundary, then so you can think of these subset of, I think I had a different picture there, but the subset of entries, yeah, we drew it here. So, so the subset of entries is a kind of a projection of this cone on a subset of coordinates. And if you happen to lie on the boundary, then, just having the positive semi-definite conditions could result in having, only a particular rank possible for the point configuration. So in other words, even without explicitly restricting the rank, and you simply say it's a distance matrix, there are situations when which you could end up with finitely many solution or unique solution or whatever. And another way to interpret that is that the Cayley-Menger inequalities force an equality. So the equalities then bound the rank, and the inequalities are just saying that it has a real realization. Okay. So another question that you're interested in, besides whether or not they exist, et cetera, is suppose you wanted to find the realization, what is the, or even determine the realization algorithmically, determine the existence of a realization algorithmically, what is the computational complexity? So the overall, all of these questions, they depend on the graph of the entries of the partial matrix, and to what extent do they depend, and do we care about more than just the graph? Okay, so so let's see how the dependence on the graph sort of manifests itself. Okay, so let me just go to the whiteboard for a second. Okay, so since we already saw the one proof, the proof that we gave of the Cayley-Menger conditions used a kind of an algorithmic approach that you are finding the realization at the same time checking the Cayley-Menger inequalities, or you can think of finding the realization as checking the Cayley-Menger inequalities. And let's just think about how that that proof actually worked. So the proof involved finding intersections of spheres. And let's assume for a moment, it doesn't matter, eventually it generalizes to every dimension, but let's assume for a moment that our points live in R2 for a second. So there exists a realization in R2. If you remember that algorithm, the algorithm just finds the dimension of the realization at the same time. In fact, it finds the minimum dimension of the realization as it tries to figure out, as it figures out whether or not any realization exists, or in other words, whether the given matrix is an Euclidean distance matrix. The only difference is when we gave that particular algorithm, we didn't think about whether all the entries were actually given in the matrix. What I'm going to point out is that if in fact the dimension of the point configuration is bounded by some number d strictly less than n-1, we are not going to use all the entries just to find a realization. Okay, so let's for a moment assume that d is actually equal to 2. That algorithm basically would place 2 points with the first distance between them. So there's a partial, I'm going to show you that it's only a partial set of entries is sufficient. So we place the first 2 points without loss, put this at the origin, without loss, put this at 0, comma, or d1, 2, comma 0, right? And then we place the next point, and to place the next point, we just needed potentially these 2 distances. And so this is the third point. So this is d1, 3, and d1, 3, and this is d2, 3. So we only needed these 2 distances. So far, yeah. And then when we place the next point, remember at this point, we are not trying to verify whether a complete matrix is a Euclidean matrix. We are just trying to find a realization. And the question is how many of these entries do we actually need to find a realization? So let's say if there's the 4th point, we can place that 4th point using any pair of other distances. So you can choose whichever pair you want. So potentially you could have chosen this pair, or you could have chosen that pair, right? So essentially you place that point finding these 2 distances. Okay. Now the 5th point, now notice that this distance between 3 and 4 is something that we did not use. Keep that in mind. So now to place the 5th point, now remember that the 4th point could have been placed over here, or it could potentially have been placed over here. I'm going to use a different color. Could have been placed over here.
Can I ask a question?
Yeah.
Just a reminder, when we were placing the 3rd point, how did we solve the system of 2 quadratic equations in 2 variables?
It becomes just a single quadratic. I'm going to leave that as a homework. It just becomes 1 quadratic in 1 variable. Doesn't matter. You could solve 2 quadratics in 2 variables, but you can reduce it to 1 quadratic in 1 variable.
Okay, thanks.
Yeah. So the 4th point, again, it becomes 1 quadratic in 1 variable. If you just did this. There's a possibility, we'll see it in the 5th point in a second. So it's still 1 quadratic in 1 variable and only depends on the original distance d1, 2 over here. So now 4th point could have been placed over here, in which case the distance between the 3rd point and the 4th point would be potentially different. And if you were interested in verifying whether this was a Euclidean distance matrix, you would have to check whether that distance was the distance that was given. But for the moment, we're just asking how many distances do we need in order to even find whether there exists a realization. Okay, so now let's look at the 5th point. So now the 5th point, again, you can use any pair of distances, so let me take a slight change. Instead of I could have just used these two distances, but suppose those two distances are not given. Suppose D1, 5 and D2, 5 are not given here. They're not present in this matrix. And suppose D3, 5 and D4, 5 were given. So you have these two, okay? Suppose those were the two numbers that were given in this matrix and the rest was not. So now notice that whether or not 5 can be placed could potentially depend on whether I put 4 over here or 4 over there, right? It could be that the distances between 3, 5 and 5, 4 do not satisfy the triangle inequality had I placed 4 over here. So now we need to know, so now it tells me that offhand, in order to verify where to place 5 and not have to go back and change the position of 4, we could do that. We could change the position of 4. There are two possibilities for 4. We could change the position of 4 in order to be able to place 5. We can do that. But notice that if I had been given the distance 3, 4, then I would have right away in the beginning decided which of these two positions of 4 to choose. You can convince yourself that not both positions of 4 would, I don't want to use the word generically yet, but in general, not both positions of 4 could satisfy a given distance for 3, 4. Okay, so 3, 4 has only two possible values once 4 has been placed. It's a fixed finite number of possible values for 3, 4 once 4 has been placed, given that I've said that the dimension here is 2. So in a way, this dotted line is dependent on the other distances. So once I have placed 4, I've used all of these distances. These distances determine what the distance between 3 and 4 are. So then we go to the next. So if I knew 3, 4, then I would have placed 4 in the right place. So the complexity of solving this would have been a lot simpler. I would have known where to place 5. Otherwise, I would have to check both positions of 4. You can still do it, except you can see that you might end up with an exponential increase in complexity as you place more and more points. By the time you come to the nth point, every single point before it has 2 possible values. And so by the time you get to the nth point, you may have to check 2 to the n minus 1 possible positions for all of the other points to check whether the new point is there. On the other hand, if I'd given this distance, then I know right away where to place it. So this one extra distance at every given stage makes a big difference to the complexity. So 5 is given. Again, 5 can be placed over there, or 5 can be placed over here. Right? And depending on where it's placed, if I had one more distance given to me, doesn't matter which one, right? Suppose I had been given the distance between 1 and 5, or for example here, 1 and 5, right? Knowing that distance, I can choose between the two placements of 5. So as you can see, there is a particular type of graph of distances. Had the graph, the particular ij entries that were given to me, if there's these particular graphs, as you can see, every time I add a new point, it's connected to the old graph by 2 distances, and it doesn't matter where, which of the two, the new point is connected to any pair of 2 points before. And if I'm given a third distance, yet another distance, then in fact my complexity of solution also drastically drops from exponential to linear, right? So the actual graph makes a big difference as to whether I can do this. If I weren't given this. So these are called, there are many words for this type of graph. They're called zero extension graphs or Henneberg zero extension graphs. And the type of graph that I'm not drawn. And when I have a third thing there, they're called Dilateration graphs. Okay, so now what do I mean by D? I've only been talking about D equals 2.
And what's the third thing?
The third thing? What is the third thing?
That's what you said.
The third distance.
The third thing is dilateration.
Henneberg
Repeat
is one
that,
of them.
Alex. Could you repeat
Henneberg
that,
is
Alex?
one, zero extension graphs.
Oh, sure. I was just asking because you said, and when I have the third thing, then we call it dilateration. So my
the
question,
third, remember when we were adding each point, I had a third, if I had a third distance available, if the graph allowed me, so when I placed the fourth point, I had not only D14 and D24, but also I had D34 available here in my matrix or graph.
oh, I see. Okay, thank you.
So and what is D here? So I started out with D equals 2, but notice that this can, from our original sphere intersection algorithm, this D can be anything. It could be, D could have been 3, and in which case, to place the first point, you would have intersected 3 spheres. So you would have 3, you would start out with 3 points. Once after you have 3 points, the fourth point will have 3 distances to place it in one of 2 possible positions. And you would need a fourth distance to decide which of those 2 positions to go, right? So this idea of Henneberg zero extension graphs is extends or is a general definition for any D, except that as the dimension grows, the number of edges that are needed to place the new point increases by 1. And correspondingly, the dilateration graph has 1 more distance than is needed for the Henneberg zero extension graphs. So those Henneberg zero extension graphs allow us, if the partial matrix had entries corresponding to these either Henneberg zero or dilateration graphs, in the case of Henneberg zero extension graphs, you can find a realization in this simple way, although it may take exponential time. But if they were dilateration, then you actually have linear time. The same sphere intersection algorithm that we had now gives us a solution. Notice that there are tons of entries here.
Sorry, would this be wait, what D are we taking? Is this a zero lateration if we're in R2 or?
Oh, okay. So let me just give you the word. So for D equals 2, I think, oh, sorry, this would be D plus 1. So for D equals 2, these are called trilateration graphs because we need 3 distances at any stage.
Okay.
Yeah. Okay.
If you're going to get through, then that's fine.
And in general, for D, it'll be D plus 1 lateration graphs. But these are always called zero extensions for some reason. It doesn't matter. It's just called zero extension for dimension 2 or zero extension for dimension 3, whatever.
Okay, thank you.
Okay. Because the 1 extension means something else. We'll come to that later. So they're always called zero extension. You just specify the dimension, whatever it happens to be. So so as you can see, the ability to realize or coming up with a realization and how quickly you can come up with a realization depends on what graphs are given here. So if I wasn't given such a graph, such a nice graph, then who knows how you can do this, how to do this. You certainly can't do it with this sphere intersection algorithm.
Can I ask another question?
Yeah.
For D equals 3, intersecting 3 spheres, can that also be reduced to 1 quadratic and 1 variable?
That's a very good question. I don't think so. It'll be 2 quadratics and 2 variables.
Okay, thank you.
Okay, but at any given time, you can do this. I'm jumping the gun. I'll be all over the place if I get to that. It's related to what is called triangularizing a quadratic system. Okay, so, but that's several slides into the future, so I don't want to go there yet. Okay, so another thing I wanted to talk about is slight variation on these graphs. These are called Henneberg 1 extension. Slight variation on these graphs are called tree decomposable graphs. So I just want to talk about tree decomposable graphs for a second. So tree decomposable graphs are, instead, just imagine for a second, as we just said, we can, whenever two distances are given, so here's a point, whenever two distances are given for d equals 2, you can place this point. Now, this distance doesn't necessarily have to be a given edge. It could be that there is an entire set of submatrix of this distance matrix that allows you to find a graph, find a realization of a subgraph, which I'm drawing in this way. And similarly, there could be another submatrix that allows you to find a realization of a subgraph in the way that we just talked about, and three such subgraphs. And once we have those three such subgraphs, we have our three required distances. And then we can place this point. So having found this subgraph and this subgraph, we have these two distances. Now we can somehow find the common realization of the three subgraphs. This is sort of realized in its own coordinate system, let's say, and this has been found in its own coordinate system. Now we have to sort of put them together to find a joint realization of everything together, and you can do this. So this kind of graph, which is recursively defined as being, this is called a tree decomposable graph. It's recursively defined as being three tree decomposable graphs, each sharing exactly one vertex. Okay, and the base case, a tree decomposable graph, is just an edge. So tree decomposable graph, the base case is edge, and in general, three decomposable graphs, each pairwise sharing a vertex.
Is that 3 for all d, or is that d plus 1?
Yes. So this would be d plus 1 in general.
Okay, thank you.
Okay, sharing a vertex. Okay, so so this is called a tree decomposable graph in general for any dimension. So that's a sort of a natural generalization of these Henneberg 1 and Henneberg 0 and the corresponding trilateration or delateration or d plus 1 lateration would now have one more distance that you can use at any given stage. Okay, so I'll just define tree decomposable for now. Okay, so these tree decomposable graphs are very commonly, so now that you brought up the question, Alex, I'm simply going to talk about this idea of solving the degree of these things. So we'll come very quickly in a few slides to the idea of solving polynomial systems. And here we are solving a whole bunch of quadratics, which correspond to the distances, the distance map that we talked about. These are not you can alternatively think about this as solving, as we did in the original algorithm, where we thought about the sphere intersection as finding as taking a Cayley-Munger determinant and setting it to 0 is exactly the same as solving for the sphere intersection. One is taking place in the distance coordinates. These are the Cayley-Munger matrices where these are the distance coordinates, and the other one you're solving for the distance coordinates directly in a way. And in the other case where you're writing all these equations down, pi minus pj distances equals something, the given Dij squared distances. So you can think of what we're doing, the sphere intersection algorithm, as solving two types of polynomial equations. One that involves the distance map, the polynomial distance map, where the distances are given, the partial entries of the matrices are the right-hand side, and you're writing all these equations down. Another way to think about it is that you're directly solving for the the unknown distances of the partial matrix by taking the Cayley-Menger determinants and setting them to be equal to 0, with where the known values are, sort of given in here, and then the determinant is a polynomial in the unknown distances, or you're solving for those polynomials. You can think of it as either way. This case, of course, quadratics, no matter what the dimension of the point realization, this is always quadratic. Whereas if you did it this cumbersome way, obviously, depending on the dimension, the determinantal degree is going to increase. So this is just a curiosity. It's a way to think about it, but this is how you want. For checking is a different story, but for actually realizing, you want to use the quadratic system, this polynomial system, to solve. Okay, so Alex's question, so you have a whole bunch, these are obviously the number of variables that are the coordinates of these points. There are going to be d variables here and d variables, so that this is a multivariate quadratic system. And so what you're trying to do is solve this system, and there are many ways to think about solving this system. And one of the most common ways is called a Grosvenor basis method. And we'll come to that in much more detail in a few slides. Right, and what the Grosvenor basis is a kind of generalization, if you will, of Gaussian elimination. It can be thought of as generalization of, sort of GCD. It can be thought of a generalization of Gaussian elimination. Right, and what does Gaussian elimination do for linear systems? For linear systems, if you have a bunch of equations, linear equations with let's assume they're 0 on the right-hand side. For now, it doesn't matter. Could be something on the right-hand side. You triangularize it. You triangularize the system. And with Gaussian elimination, when you triangularize, nothing happens to the degree. The degree doesn't increase, right? They still remain linear. The key thing is that each time there's one variable here, and there are two variables here, and there are three variables in the system, and so forth. So you can sort of back substitute, you can solve, you have one variable equals something, and then once you have that, you can put that here, and again, you have just an equation in one variable, and again, you have an equation in one variable, and so forth. So in our situation here, when we were solving here, we basically solved for 3. So solving these two quadratics, we gave, and that's a univariate system, you get a solution for the coordinates, so that when you're solving the next quadratic, it turns out to be again a univariate quadratic because you've already substituted for the values of this. Okay, so you have, when you're doing this, essentially you have triangularized this polynomial system, where each time you're solving with one fewer variable, and it turns out, because we have tree decomposable graphs, we actually have a triangular system where the degree does not increase. So normally when you do Grosvenor basis or anything else to actually triangularize a system, unlike the linear case, as you go down here, this polynomial will be a univariate polynomial, but it'll have a huge degree. Typically, whatever this n is, it'll have some exponential degree in that. Okay, but the tree decomposable systems are ones where you can triangularize and still maintain quadratics. and still have only quadratics. Still not increase the degree. Okay.
Hey, Meera.
Yeah.
So the way to reduce the two quadratics and two unknowns to a single quadratic is by Grosvenor basis, you're saying?
No. You don't have to. I mean, it's much simpler than, you don't need Grosvenor basis for that, right?
Oh, okay.
All I'm saying is that if you did the very general Grosvenor basis method, you can still triangularize, but you'll end up with the equations having very high degree. But with the tree decomposable graphs, what you have essentially done is triangularized the quadratic, multivariate quadratic system, but not increase the degree. Every time you're always only solving for one variable more or some constant. I mean, I'm not going to be very particular right now. Maybe you're solving for some constantly many variables more, right? It has this triangular form, but you have not increased the degree. Okay, so essentially having, and this is also turns out that this also, because you don't increase the degree, this is what is, in Galois, this is quadratically radical. The solutions are quadratic elements of the quadratic extension fields built one on top of the other. So this is also called quadratic radical solvable. Radical solvable systems, right? Because you don't increase the degree. So you, every time the square root, you get a square root, assuming it's real, and then you get an extension of the original coefficient field. Let's say the original coefficients of your polynomial were in the rationals or something, and you have a quadratic extension, so you have some square roots in there. And then now the coefficients of your new polynomials will now have this, and then you have, so you sort of build a tower of quadratic extensions, Q and then square, and then you're adding on some square roots, and then then you have Q and the square roots, and you're getting square roots of those and so forth. But whatever it is, you only have quadratic. So this is also called quadratic radical solvable. So when you have a tree decomposable graph as your partial matrix, you can actually say a lot of good things. First of all, you can realize it just using a triangularized quadratic system without an increasing degree. You have a quadratic radical solvable. Plus, if you have that one extra distance at every stage, you have a D+1 lateration graph, then, or the tree decomposable version of the D+1 lateration graph, you now have, in addition, a low complexity, just a linear complexity in solving for the system. Okay, so if you don't have that extra degree, you can actually show that finding a solution, that exponential growth in complexity, you can actually formalize it as an NP completeness result. That's an old result by Sachs. So he showed that just even with the tree decomposable graph, if you didn't have that extra distance at every stage, even for just a Henneberg zero extension graph, if you didn't have that extra distance at every stage, the fact that you have to check both possibilities every time can be formalized as an NP completeness complexity result. Okay, we'll come to that eventually. Okay, so now I think I have pointed out the new share. No, not this one.
Meera, let me ask, when you have two quadratics,
Okay.
Let's actually stick with the case of two circles that we're trying to intersect. So you can reduce that to a linear equation, and also one of the quadratics. You don't need both of the quadratics, really.
You don't need both the quadratics, right? Yeah. But I don't want to really be. So I'm saying, at every stage, you only have one and more variable and still a quadratic. at every stage.
That's right. That's right.
Yeah.
It's only one quadratic. There's a bunch of linears and then one quadratic that's left, right?
Yes,
that's why we
that's
get
right.
this single quadratic extension at each stage.
Exactly.
Okay, good.
And that's true
I'm tracking.
actually for any D, by the way. You just have to work a little harder.
Yes. Okay, that makes sense.
Yeah.
Yeah, can you allow us to chat with everyone? Is that possible?
Yeah. I
Is that
don't
what-
know if I can do it when I'm in Zoom. I
I-
thought that
I-
was the setting. I thought I had changed the setting to do that.
I can chat to everyone.
Stuff, can you do that by any chance? Or am I able to do that within Zoom?
Oh, I see. I wanted to chat with Will because I wanted to ask him about this linear and quadratic thing.
Oh, yeah, that's what I meant. But how do I do that?
Maybe allow private chats between two members or something.
But
If
isn't that something I need to do? I have to leave Zoom.
If
I
you
mean, sorry, I have to go log out and then go and do something in the settings.
no, we fixed it last time. If you hover over the chat symbol, there should be a little arrow
Here?
above it. You click on that, and then there
Oh,
should be
yeah,
a
yeah.
chat
Everyone
symbol.
publicly, yeah, I allow you. You can chat with everyone.
But also to individuals?
Oh, you want to
Oh.
do private chat? No, I don't want to allow that, Alex. You can talk to Will, but talk to him publicly.
Oh, okay, no problem.
Okay? Yeah.
Sorry, can I ask one last question
Yeah.
that you probably answered already? So this matrix we got here,
Yeah.
that's the triangularization of the multivariate quadratic one we had on the last slide? Or
Yes.
not?
So you're right. I can see how things can be confusing. This matrix is totally different from the matrix we started out with.
Okay.
Yeah, this matrix is the distance matrix where some of the entries of the distances were given, and these distances are the right-hand sides of our equations.
Mhm.
And this matrix is these equations which have been triangularized.
Oh, okay. So the original matrix, each one we've got is an equation of the form like pi minus pj squared equals dij squared.
Yes,
Oh,
we
these
had this. So we started out with this partial quote unquote matrix. You can think of it as a distance vector of which some of them have been specified, others have not been, right?
Yeah.
That's our graph. And each one of these entries, given entries, I'm going to make up a bunch of quadratics like this with this number here on the right hand side.
Okay.
Okay, so I have this system of quadratics, multivariate quadratic system.
Mm-hmm.
Now that is what I'm figuratively or schematically representing now as this thing. Yeah.
Yep.
Except that I have now triangularized that system.
Got it.
Okay. By, I haven't told you all the details, but I'm sort of, because that if I really want to be able to do it for an arbitrary quadratic system, I have to use more machinery. But with our example graphs that we had with our tree decomposable graphs, you can see that we ended up with a quadratic system to be solved at every stage with one more variable every time. Where if you solve the previous one, you can substitute it, and now you just have a single quadratic in one variable. Plus some linears, as Will says. Okay.
That makes sense. Yes.
Yeah. Okay. So, right. So let's go back to, okay, so I was ambitious to think that I could directly annotate this blank slide, but now I'll put the other stuff in here at some point. By the way, are you able to see the copy that I put on Piazza? I'm making copies of these, and well, we can talk about that later at the end. Okay, so some of the things that we have seen here while we did this in this simple example of tree decomposable graphs and the corresponding triangularization of the polynomial system, we noticed a few things. These extra distances for the D+1 lateration graph, as we pointed out, are sort of dependent on the other distances. So without that extra distance, you still have only finitely many solutions. At every stage, you only have finitely many solutions. So altogether, you have only finitely many solutions. And these extra distances are dependent in the sense that once you have these other distances, this extra distance is determined. I mean, is going to be one of two things, one of two numbers, because you have only finitely many solutions at two solutions at each stage. The extra distance can be only one of two things. So that's local dependence, right? So these are things that we notice here. And so this idea of dependences can actually be seen without having our underlying field and well, we talked about the reals and complex numbers. So there are numbers there, the distances are numbers and so forth. But we also talked about a graph, and we somehow said that these answers could be given, the question of whether something exists or whatever could potentially be, and what the complexity is and so forth, could be just determined based on the graph. So the question is, when is a graph sufficient to answer all of these questions? Do the distances, coordinates, etc. actually matter? Do the actual values matter? Or to what extent? I mean, obviously they matter to some degree, but to what extent can we answer these questions just by looking at the graphs, just answering questions about the graph? So this is I guess Tony has already covered generic and all this. When he talks, Tony, people who are attending Tony's class, he's already obviously talked about generic coordinates and generic frameworks and so forth, right?
Yes.
Okay. So so you already have that idea in your mind that you can answer some of these questions at least based on just what the graph looks like. Okay. So we'll go into more detail about what generic means and when can the question be completely answered with only using the graph, and when you need some other information and so forth as we proceed. But the idea of dependences, dependences between, in this case, edges of the graph, because this new edge, the third edge in a two-dimensional zero extension, with the third edge was dependent. And this idea of dependence between various things in a graph, or you can think of that particular polynomial, that distance being dependent on the other distances, or you can think of the polynomial that we had that pi minus pj squared that corresponded to that third distance being dependent on the previous polynomials. All of those three types of dependences that we have taught, that I just mentioned, either a dependence in the graph, a notion of dependence in the graph, dependence of the polynomials on the other polynomials, and dependence on distance on the other distances. All of these are, a common notion of dependence that can be captured by these, that have been captured by objects called matroids. Okay, so so matroids are a combinatorial object. So in other words, the actual field, underlying field, whether it was over the reals or complexes or rationals or maybe even finite fields, that has been removed somehow. And we want to extract the idea of dependence and in a combinatorial way to see to what extent it makes sense, purely combinatorially. So it was, back in the 30s or something, they have, thought about this idea. And so van der Waerden was interested in sort of the algebraic dependencies. And previously, of course, with linear systems, you already have this idea of linear dependence. That's a well-known, everybody has seen it, say in high school or in an early class. And we can now talk about dependencies even in combinatorial objects. And that's what matroids are. So I'm going to just brief detour into matroids because we're still in the tour of the tool stage. So we've talked about, Cayley-Menger determinants, Schoenberg's theorem, and so on and so forth. And then we have come to polynomials. And now we are sort of extracting combinatorial properties of polynomial systems in the form of graphs. And now we're going to talk about this other important tool that we talk about that we're going to use, which are matroids. And we'll think about all types of matroids over graphs, over algebraic systems, polynomial systems, over the Cayley-Menger determinants, over these distances, and different types of matroids. I think Tony would have already talked about the rigidity matroid, which refers to linear dependencies. Really, it starts out not the generic rigidity matroid, but if you think of the rigidity matroid of a particular framework where you write the rigidity matrix down, then you think about the dependencies between the rows of the rigidity matrix. These are ordinary linear dependence. And that's usually where, the best place to start in thinking about what a matroid is. So let's take the simple example of basic notion of linear independence in coming up with the definition. So we'll see what is it about linear independence, sort of the basic axiomatic things about linear independence that we can extract to define a combinatorial object that's going to be the matroid. So let's just take this 8 columns, and instead of rows of the rigidity matrix, now we're moving to columns. So of course they're linearly dependent if there exists some, we think of them as elements of some vector space. So you think of dependence in the vector space. So you have some elements of the field over which the vector space is built, such that the sum over the vectors, the linear combination of the vectors with those coefficients, those field elements, is equal to 0. That's dependence, linear dependence. So otherwise, you say that this is linearly independent. And in general, we'll deal with only finitely many such entities. So here, the entities here are the columns or the vectors. So we will in general deal, remember, we're always trying to extract what is it, axiomatically, what do we mean by independence? What are the sort of key properties of independence or dependence that we can extract and then talk about combinatorially? So one thing we can see in the case of vector spaces that every subset of an independent set is independent. If two independent sets are given to you and one of them is strictly smaller than the other, then for some element of the larger set, you should be able to take it and add it to the smaller set to get an independent extension. I mean, a larger independent set from I1. That's another simple property of vector spaces. And if you have a subset then the maximal independent sets are always of equal size. Okay. So that's another thing, you always think of bases, you can take different bases, different subsets of these vector space, that set of vectors that happen to be independent, and the maximal ones always have the same size. So in fact, I2 and I2 prime are if and only if one is a consequence of the other. And this number, the size of the maximal independent set, is the size of the basis. It's also called the rank, which we know. So we know all of these things. I'm just extracting these properties so that we can now talk about, talk about matroids in this way. So we can just take these as our axioms. Okay. So these are all just other ways of thinking about the same thing. There are multiple ways in which you can write the same axioms down, as we can see already for this case. So if we now extract those axioms and write this as axioms of a matroid. I mean, axioms that define a combinatorial object that has these properties. So you have a non-empty subset E, it was called I in the other one, some kind of, it's called the ground set. In that case, it was the columns of that matrix. In general, it's a set of some sort. And you have subsets of it, which we're going to call bases or maximal independent sets. And with the property that no basis or base properly contains another base, no maximal independent set properly contains another maximal independent set. And if you have two that are bases and one is an element of, E is any element of one of them, then you can get another element. Well, it's very similar to the other one. You drop one of the elements from B1. So now B1 is one smaller than the other base. So you should be able to find an element of the second base that you can add to it. So it's basically the same axiom that we had here. If you had two things that are one smaller than the other, you should be able to find an element here that you can add to it and get still an independent. That's exactly what this is. If you have two of the two bases, then you should be able to drop one from one basis. So then it's of one smaller size. Should be able to find something in the other basis that you can add to it and also get a base. This is also called the exchange property. So these are the two basic axioms that define one possible set of basic axioms that define a matroid. There are multiple equivalent sets of axioms that define a matroid. So going back to our example, so these are the columns. This will be the set, the ground set, and so there we had 8 columns. So any set of 4 columns form, in that particular case, a ground's maximal independent set. And I mean, in general, because you had 5 rows, you may expect that there could be 5, but in this particular case, that turns out to be only 4, because the rest are dependent. And then you have a different basis here, a different set of columns. And now if you remove the second vector in B1 and replace it with the second vector in B2, you get another basis. And you can simply verify that this is basis. So this is in that example. You can talk about this, now that we have extracted the axioms, you can think about the same axioms. What do they mean if you don't have any underlying field or vector space or anything like that? So you just have a combinatorial object, a graph, let's say. And it's another example. So you can think of the ground set instead of the columns of this, or the set of vectors, which were the columns of this original matrix in that example. You can think of the ground set as just the edges of a graph. And you can define independent sets as being acyclic. So now we can check whether the axioms are true. Every subset of an acyclic set is acyclic. And if you have 2 edge sets that are both acyclic and one is bigger than the other, then you should be able to find an element of the second one, the bigger one, that you can add to the first one and to produce a slightly larger acyclic set, right? So if you think of the, why is this the case? Because if you have 2 acyclic sets, and one of them is bigger than the other, then you can, it is possible that several of these they're on the same set of vertices. So it's possible that there are edges here in the larger one that you add to the smaller one creates a cycle. It's possible that that's the case. But then because this is a strictly bigger, you should be able to find one that does not create a cycle, because there's one, it has to involve one more vertex, and so you can add to it and you get an acyclic set. So this also gives you the idea of a rank in the set of edges, which is the size of the maximal spanning tree. It's typically called a maximal acyclic graph that actually spans is a spanning tree of the graph. All the people in would have heard of a spanning tree, even computer science people use spanning trees all the time. So a spanning tree would be such a maximal independent set in this matroid. So this is a totally combinatorial generalization or extension or an analogy of the vector space, the linearly independent vectors of a vector space from which we extracted the axioms that define a matroid. Okay, now there's you can go from linear independence to algebraic independence. That's what Van der Waerden was looking at. So an algebraic matroid, by the way, all the references, as I said, all the sources that I use, I usually put right in the beginning of the topic, right? So there's wonderful lecture notes out there. So my job is to go and pick little bits from each one that sort of follow the flow of my lecture. So that way you can go and look up some more details that they might be giving. So you can think of, you can define this notion of dependence or independence from going to algebraic independence. So this relates to this notion of genericity that we're going to talk about in a bit. So if you have a field extension, so in this particular example, we're going to take the field to be so Q, and these are the polynomials over, so it's rationals, the polynomials with rational coefficients in two variables, and we consider the ground set given by the following polynomials. So the ground set of these polynomials. Now we can think of the the dependent and independent subsets in the. I have to decide which order to do these things. So it's algebraically independent if there is no non-zero polynomial such that P with alpha 1, alpha 2. So some other polynomial of these polynomials that is identically zero. Okay, so if that happens, then these are said to be algebraically dependent. If it doesn't happen, so we're going to, this is the notion of ideal, which we're going to talk about very quickly, but very soon in the next slide or something, but next two slides. But this tells you what algebra, so you can look here and verify for yourself that the independent subsets of this set, this ground set are given here. And as I said, there are many different types of axiomatic definitions of matroids. And so in this book, this is a book by Rosen. He has actually specified many examples where all the different types of bases, different types of axioms that are used to define matroids, the relevant objects have also been defined. Okay.
Dr. Sitharam?
Yes.
So when you have that independent set 1, 2,
yeah,
is that saying that there's no polynomial?
No polynomial, yes.
Whose coefficients are alpha 1, alpha 2?
No. So you can think of a polynomial of these polynomials.
Okay.
Yeah. So so these are algebraically independent if there's no polynomial of these that is equal to 0. So P is in this extension where K is Q, right? So K would be rational coefficients with rational coefficients.
Okay.
Is E here K extended by A1 through A4? Or is it just those 4?
A1 through A4, alpha 1 through alpha 4, yeah.
Yeah, sorry, alpha 1.
Yes.
He is the finite set, yeah?
Yeah.
Okay.
Yeah.
Thank you.
We're always, we're never going to look at infinite, whenever we're talking about matroids, our ground set is always finite.
Okay, thank you.
Yeah. So what types of polynomials? Okay, I think we asked this question two lectures ago. So we have certainly seen the distance polynomials, the quadratics, the simple quadratics. We have seen the Cayley-Menger polynomials, those in our discussion so far. We have seen these two types of polynomials. One is quadratic, one is not quadratic, but so one of them, and Will already pointed out, the Cayley-Mengers are syzygies of the distance polynomials. So they're polynomials in the polynomials, in distant polynomials, so to speak. And we have already talked sufficiently about the dependencies between the Cayley-Menger relations. And we now talked about dependencies between the distance polynomials. So we have seen, and correspondingly, there is a notion now, because of matroids, there's a notion of a dependence of an edge of a graph on the other edges of the graph. In the tree decomposable graph, if you add that extra edge to give the D+1 lateration graphs, that extra edge is now correspondingly dependent. Okay, and so I haven't told you in what sense what the new matroid is over the graph by which you get that dependence, but you can imagine that that's the case, and I believe Tony might have talked about this in the sense of generic rigidity matroids. Okay, so by the time we come to the generic rigidity matroids, we would have already gone through some of the other things about polynomial systems. And we would have finished this tour of techniques before we actually go into those. So again, for polynomial systems, what do we care about? Again, we care about the existence, whether it's zero-dimensional, is the solution unique, and under what assumptions on the polynomial systems. So we think about what are called generic polynomial systems. Very briefly, this would mean that the coefficients of the polynomial systems are not the zeros of some polynomial, right? So they're the coefficients, which are just elements of the rationals or reals or whatever, are in our examples that we have seen so far, the coefficients are themselves just reals or rationals, so that they don't form the zeros. They are not the zeros of some other polynomial. Okay, so that's what we mean by generic. And then you have non-generics, questions that you can ask about without having the genericity assumption, that you have a specific polynomial system and you want to know about the solutions to that, whether they exist, they are zero-dimensional, unique, etc. So you could ask two types of questions: generic questions and not general questions, which are not necessarily under the genericity assumption. Okay, so now to complete the tour of techniques, the last one before we start going deeper into the different topics is going to be solving polynomial systems. Okay, so the key sort of things that we're going to visit over the complex numbers and again over the real numbers are some things like this. Okay, so first is Bezoot's theorem, and this is taken directly from the Wikipedia page on Bezoot's theorem. It's simply what you would expect, which you learn with when you talk about linear systems all the time. You look at the number of polynomials and how many number of equations and number of variables, and then you say something about the number of solutions. So in the original form, the theorem basically says that in general, what does in general means? Generically, the number of zeros equals the product of the degrees of the polynomials. And so if you have n polynomials and n determinants in certain degrees, so the number of zeros equal to the products of the degrees of the polynomials. Okay, so and that's generically speaking. So it's not always the case, depending on the particular polynomial. So in the modern formulation, it's saying that if you have n projective hypersurfaces and it's an algebraically closed field, so we're talking about the complex numbers as far as we are concerned, and you define their homogeneous polynomials in n+1 indeterminates, then either you have infinitely many points. So in other words, these hypersurfaces meet on an infinite dimensional solution, or if it's finite, it's equal to the products of the degrees of the polynomials. Okay, and moreover, you know, the meeting points of these are not higher dimensional in general. Generically, it's always finite. Okay, so it's like saying that in general, if you take two linear, I mean, it's very rare that you end up with, it's measure zero that you end up with dependent equations and with the right number, and that's what this is saying. So Bezoot's theorem is fundamental in computer algebra because it shows that most problems have computational complexity that's at least exponential in the number of variables. So essentially it's saying that because you have, that sort of gives you a lower bound on what you can possibly expect. If you want to find all the solutions, you're going to end up with some exponentially many, since there are exponentially many possible solutions. So essentially you will end up running your algorithm, whatever it is, in order to find all the solutions, is going to be an exponential time. So that sort of gives you what to expect, you know. So when you're solving polynomial systems and you want to find all the solutions, you're going to end up with very algorithms that run for a long time. So two of the common usual suspect objects that you have to think about when you're solving polynomial systems are varieties and ideals. There's a nice book by Cox. It's called Ideals and Varieties, and it has very computational treatment of these things. And it's I would really recommend looking at that. But I'm going to take a bunch of notes and slides actually from Pablo Perillo, who's one of the organizers of this thematic program. So this is actually from Wikipedia, as you can see. So an algebraic variety, in the usual simple way of thinking about things, classical way of thinking about things, is that it's just the system of solutions, the set of solutions to a system of polynomial equations over the real or complex numbers. Usually they mean complex numbers. So we can, sort of think about, this is the easiest way to think about varieties as simply the solutions, the set of solutions to a system of polynomial system equation. So these are two examples here. I don't know if you see this or it's too small. So on the left is defined by the equation x squared plus y squared minus 1 times 3x plus 6y minus 4 equals 0. And you can see that taking the product of two polynomials and setting that to be equal to 0 is the same as saying that both of, so at least one of them has to be 0. So at least one of the two polynomials has to be 0. And the first polynomial represents the circle because it says circle of radius 1. And the second polynomial represents this line. So essentially this union of these two is exactly this, the set of all xy values such that the product is equal to 0. So the product is equal to 0 if either one of them is equal to 0. So that gives you the union. And the one on the right is the quadric surface defined by 1 minus x squared minus y squared minus 2x squared plus z to the 4 equals 0. So they can look really weird. You can see that this is, you can factor this and see that, convince yourself of that. And you can, with Mathematica or Maple or whatever, you can, even MATLAB, you can draw a lot of these that are solutions to simple polynomial systems. So formally, if you define algebraic varieties, the zero set of a finite collection of polynomials, and this is defined as follows. So if you have polynomials in over the complex numbers, the variety is the set of all elements such that f of, those, if you plug those in for the variables, is equal to 0 for every one of these f's. That's called the variety defined by this set of polynomials. Okay, so this is related to the notion of ideals. And so essentially it's an ideal, again, defined by a set of polynomials. A variety is defined by a set of polynomials. An ideal is also defined by a set of polynomials, saying that if an ideal in general is that if something belongs to the ideal, so 0 is in the ideal, and if 2 elements belong in the ideal, then their sum is in the ideal. And if an element is in the ideal and you have b over the another polynomial, so this is a polynomial, this is another polynomial, then their product is also in the ideal. So you can take any polynomial combination of polynomials and that will be in the ideal. So so for our purposes, the important examples of polynomial ideals are the ones that vanish on a given set. So that's going to be all of the polynomials such that vanish on the zeros of a given set of polynomials, right? So that's going to be one of the key things that we're going to care about. This is called the vanishing ideal of S. S is a set, and typically that set is taken to be the roots of another set of polynomials. And the ideal generated by a finite set of polynomials, which is simply the sum, the polynomial combination, some polynomial combination of the given set of polynomials. That's what this is. So, so there's definitions of principal ideals and finitely generated ideals, which you can look up. Okay, so so there's an important theorem called the Hilbert-Bezos theorem that says basically that every polynomial ideal is in fact finitely generated, which means that you can, so the definition of finitely generated means that you can write this down as using a finite set of polynomials, right? So if you have an ideal, you can always write it down using a finite set of polynomials like this. So every polynomial ideal is in fact finitely generated, and we are going to use Grosvenor bases, which is one form of the generators of an ideal, and which makes it very convenient. As I said, it's related to triangularizing polynomial systems. I mean, it's the analogy in polynomial case of triangularizing linear systems. So think of it as a Gaussian elimination type procedure. So that gives you a nice sort of triangular basis that generates the given ideal. And so now the question becomes, okay, given a polynomial p and a bunch of other polynomials that determine an ideal, so you're given p and you're given a bunch of f1 to fn, and you want to see if p can be written as a polynomial combination of f1 through fn. So these are the two important questions and very difficult questions, and they're closely related to finding solutions of polynomial systems. Okay, so Hilbert's Nullstellensatz actually connects ideals and varieties, at least to the extent that we care about them. So given a finite set of polynomials, we know how to generate the ideal, and we also know how to look at the corresponding variety. So variety is the set of places where they all vanish. The ideal is all the other polynomials, which can be written as polynomial combinations of these. And you can, one direction is very easy to see is that, you know, if f1 through fn, f1 through fn minus, well, okay, it's saying here. So how do these ideals relate to each other? If you look at the vanishing ideal of this, which is all the ones that vanish exactly when all of these polynomials vanish, and how is that related to the ideal that's generated as polynomial combinations of these polynomials? Turns out that they're exactly the same. So it's saying that if you look at all polynomials that are polynomial combinations of these polynomials, that's going to be exactly equal to the set of polynomials that vanish exactly when all of these polynomials vanish. Okay, not exactly. So they vanish whenever all of these polynomials vanish.
We need some kind of radical assumption here. Yeah.
Say that again.
I think we need that the ideal generated by f1 through fs is radical. If you want this, if you take an ideal f1 through fs and look at its zero set, and then look at the set of all polynomials that vanish on that ideal, it's in general not the original ideal. It's the radical of the original ideal. So if a power of a polynomial, for instance, vanished on the original
yes.
ideal.
Okay. Yeah.
Right? So I think this is just a tiny
Yes. Yes.
caveat. Yeah.
Yes. 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 I see.
Complex values need, yeah. So x squared, for example, generates all polynomials that have a double root.
Yes. Yes.
But in the
I'm glossing over a few things here. Okay. So this equality, one direction is very easy to see. We pretty much already talked about it. But the other direction is basically the theorem called Hilbert's Nullstellensatz, and I'm giving you a weak version of this from Wikipedia. So you say that ideal contains the constant polynomial 1 if and only if the polynomials do not have common zeros, any common zeros in this Kn. So it's another way to formulate it is I is a proper ideal in K1 to Kn, then V of I cannot be empty. I is there exists a common zero for all the polynomials and the ideals in every algebraically closed extension. And we're important to note that this Hilbert's Nullstellensatz, even the weak Nullstellensatz, requires this algebraic closeness of this field here. Okay. So, a counterexample, if you're looking over the reals, is this case. Okay. So one thing that we want to, for those of you here who are used to linear programming and optimization, I know there are several of you there. One of the key things that I want to show an analogy that runs through the whole next few slides is going to be this idea of duality. So usually when you're trying to see if there exist solutions, and you say that the set of solutions is empty, if and only if you can find lambda and v here. What was that noise? I hope I'm not losing power. No, everything looks fine. So essentially this is saying that if saying that there is no solution to a system of inequalities and equalities, let's say, in linear programming duality, this is essentially saying that the dual program, so there is a lambda and v such that this is satisfied. Okay, so those of you who are used to linear programming, this is one of the most common things that you use all the time. So showing no solution exists is equivalent to saying that some solution exists to another system. So the Hilbert's Nullstellensatz can be thought of as, or at least the weak Nullstellensatz to the extent that we're going to use it, can be thought of as a similar sort of statement. It's saying that, the set of solutions to a polynomial system, complex solutions to a polynomial system, fi, I going from 1 to m or whatever, of z is equal to 0, that set of solutions is empty if and only if the constant polynomial is in the ideal generated by those polynomials, right? So one direction is, again, as we talked about, one direction is essentially a restatement of this statement here, right? One direction is kind of straightforward. If, if 1 is in the ideal, then you could not have written, since 1 cannot be written as, if they vanish, if they have a common 0, you could not write 1 as a polynomial combination of them. So the other direction is the hard part. So this is also the same as saying, so 1 is in the ideal, and by the definition, by the equality of the vanishing ideal and the ideal is just saying that there are some multiplying polynomials such that you can demonstrate basically that 1 is in the ideal by writing 1 as this polynomial combination of the original polynomials. So the non-existence of a solution comes down to finding the existence of these multiplying polynomials such that this adds up to 1. So that's that duality, that this similar sort of showing non-existence of a solution comes down to finding this, and you have a similar situation here. Okay, and so I'll talk about complexity and all that a little bit later. Okay, so in this context, you can think of this job of finding these QIs, this multiplying polynomials, so to speak, such that f this is equal to 1. If you want to establish that there is no solution, one of the ways to do that is to use these Grobner bases, right? So in other words, you are going to take your set of polynomials and massage them into a form so that finding this becomes easy. Okay, and this is a sort of an expository article written by Bernd Stomfels in, I believe, American Mathematical Monthly, where he talks, and there are many others, by the way. In fact, I was going to recommend John Perry's slides from University of Southern Mississippi. I didn't put the link here. The reason I didn't put the link is because if you click the link, it'll say it's a bad link, get out of here, and all that stuff. It's insecure and so forth. But I actually have that link here. And he has a very nice set of slides that actually go through the whole situation, Gaussian elimination for linear polynomials. What exactly do you do? You sort of find a type of greatest common divisor to do the triangularization, and he does the whole parallel development of the whole Gaussian elimination and GCDs for polynomial systems, and that sort of I find that to be a very good source to get examples to do this. Okay, so today I'm not going to do that. As I said, we're still in this tour, and today I hope to finish this tour so that we can start going into the details of the different topics as we and so I don't want to go into the detail of a Grobner basis example, which we will definitely do. But I want to quickly talk about what do we do with all of these things over the reals, because remember, we started out with having real symmetric matrices that represent the distances, and we want real solutions to the polynomial that represent either the Cayley-Menger equalities or the polynomials, the distance polynomials. So all of this stuff that we have talked about over the last 3 or 4 slides, or maybe even 6 or 7 slides, with the ideals and varieties and everything, is over the complex numbers, algebraically closed. Hilbert's Nullstellensatz requires algebraically closed, and so forth. But we care about real solutions. We want to ask whether there is a real solution to a system of polynomial equations, not whether there's a complex solution. So this weak Nullstellensatz that we had, we need to get a form of it that we can actually use for solving for real solutions. So, so in other words, we have in the linear case and in the nonlinear case, we have, we have LP duality if you have linear systems, inequalities, and so forth. And in the polynomial, the complex, we have Nullstellensatz. And the question is, what can we do over the reals? If you have polynomial systems over and we want real solutions, what do we do? Okay, so one of the things that you might expect when you're trying to find real solutions is you have discriminants, right? So if you just have a single quadratic in univariate quadratic to check whether it has a real solution, you have a discriminant polynomial in the coefficients of the original polynomial, and you're going to check whether that's non-zero. So checking inequalities is sort of fundamental or integral and almost equivalent when you want to find real solutions. So whether you're finding real solutions or whether you're dealing with inequalities and equalities, polynomial equalities and inequalities, essentially the problems or the complexity is more or less the same. So this basic problem, as if you're given a polynomial and you want to check whether it's non-negative everywhere, there's a very basic problem that's going to come up when we're trying to find real solutions. Is how do you determine that? You can do all kinds of quantified elimination and all that, which takes forever. But we want to sort of see whether there's a simple way to do this. And there's a simple sufficient condition for f to be always non-negative, is that it's what is called the sum of squares. This is a very key technique, and just be patient. It seems that I'm going all over the place, but this is going to make full circle and connect it to something that we've seen before. So that's why I want to go through this today. We're already at 11:38. Okay. So we can, in order to check whether a polynomial is non-negative everywhere, we're going to have to do things like this when we want to find real solutions. One of the key ways you can do this is a sufficient condition. It's not often necessary. Check whether it can be written as a sum of squares. And it turns out that almost all cases, it's actually necessary. There are, of course, counterexamples. Okay. Now, can we compute this sum of squares decomposition, so to speak, efficiently? And we come to something very familiar that we have already seen, the positive semi-definite cone. So the Euclidean distance cone, which we saw, which is the negative semi-definite cone, but the corresponding Gram matrix cone is exactly the positive semi-definite cone. So what we can, in order to determine, so just a recap of what a semi-definite program is. Semi-definite program is simply that you want to find, given some symmetric matrices, AI, and you have the trace of AI x to be equal to BI, and this is given that x has to be, positive semi-definite. And so the question is to find whether it's feasible. Feasible means you want to find whether there exists, whether this thing is non-empty. Okay. So this is basically the intersection of an affine space and the self-dual convex cone of positive semi-definite matrices. So it's a broad generalization of linear programming, and it has nice duality theory because things are convex. You can use all the tricks of the trade from linear programming, the duality that we talked about, and all of these things. And essentially, since there's no rank condition, there's nothing that you're saying anything about in ranks of any matrices. It's essentially solvable in polynomial time. Okay. So because there's no rank, so it's like saying that I am only saying that I only have the positive semi-definiteness condition. So in other words, I want to find a realization in some dimension. Does there exist a realization of which the given matrix is a Gram matrix in some dimension, right? So so basic method, which is called the Gram matrix method. So given fx, you can determine that, so Z is a suitably chosen vector of monomials. In the dense case, all the monomials you're going to need. Remember, we're trying to get an SOS or sum of squares expansion of a given polynomial to determine whether it's non-negative. So you just write, you can say that f is a sum of squares if and only if f of s can be written in this fashion, and you can solve it using a semi-definite program, and where Q can be factorized as L transpose L, because you have, if it's written as a sum of squares, you're going to have non-negative eigenvalues. So you can write Q as L transpose L. Just like, remember, we did the whole proof right in the beginning of Schoenberg's theorem, and all those ideas are here. Okay, so here's an example. F of xy is in this way. You can write it in this. You want to check whether it's the sum of squares polynomial. You simply do the semi-definite program. You just say that it can be you're looking to see whether there's a PSD matrix here. So Q has to be PSD. And so in order to solve for it, you just solve the semi-definite program that requires that this has non-negative eigenvalues or singular values, if you will. And then you just find L using SDP, and then that gives you the actual expansion of F as a sum of squares polynomial. Okay, so so now going back to the Nullstellensatz, we want to have a question. We now are asking the question whether it has a system of whether a system of inequalities and equalities polynomials has real solutions. And the answer is something called Positivstellensatz. And it's a common generalization of Hilbert's Nullstellensatz, or at least the weak version, and LP duality. And this idea of infeasibility certificates is just what we talked about, which is that in order to show that something does not have a solution, you sort of show the existence of these multiplying polynomials. So these are called infeasibility certificates. Multiplying polynomials, so that demonstrate that one is in the ideal. In the case of Hilbert's Nullstellensatz, it's a similar idea here. Okay, so Positivstellensatz simply says that given this polynomial system where you're looking to find whether there are real solutions to it, you define the cone of Fi as the sum over Si times the products of these guys, and the ideal of Hi to be the sum over Ti, where in particular these multiplying polynomials are sums of squares. So they have to have that sum of square condition. So to show that this is zero or does not exist or empty, sorry, the set is empty. So essentially we find F in this cone and H here such that F plus H is -1. So this is the analogous version of Hilbert's Nullstellensatz, right? So so this allows us to get certificates, so that duality that we had, that whole between, in the case which we had for linear programming and which we had for complex or algebraically closed fields, and answering this question, what can we do for polynomial, real cases, whether there exists a solution, whether we have a similar duality, and that's what we have here. So it says that we have real solutions to polynomial equations and inequalities, or do not have is empty, if and only if you have these F and H, where F plus H is -1, F is in the cone, and H is in the ideal. And you remember that in the definition of the cone, we had these SIs, which had to be sum of squares. And checking sum of squares is just an SDP problem. So the set of emptiness proofs is convex. So the key thing is that if we had bounded degree, then we can find the certificates, which is these guys, by just solving semi-definite programs. So I think that sort of completes our tour. We've done graphs, matroid, polynomial systems, over the reals, over the complexes, and the importance, Cayley-Menger, Schoenberg, the key things about the maps between point configurations and distances, and the things to watch out for. I think we have completed our tour. So what we're going to do next, starting from Thursday, is go into each one of these topics in detail. Okay, I'll stop here and take questions. Sorry, I raced through the last bit, but I didn't want to go on forever with this tour.
Thank you.
Meera, you mentioned the Wu-Rit method.
Yes, I have. We will do that. Yeah,
We'll
we will
get
do
to that
Grosvenor
later.
basis and Wu-Rit in some detail. Yeah.
Okay, excellent. Thanks.
Yeah.
I'm curious about that.
Let me see if there are any questions for me on the chat. Good place to learn about the topics. One is some combination of the ideal, certificate of infeasibility. Good.
Hi, Meera, I have a question.
Yeah.
so about a question about the projection of the EDMs, right?
Okay. Yes. That's going to be probably the first topic I'm going to get into deeply.
Sorry?
Now that we've finished our tour, okay, go ahead. Ask me the question. Here's a projection picture.
Yes. So you project, suppose you have a graph E.
Yeah.
And then you have and then this graph has a dimension E minus K in the rigidity matrix.
Yeah.
In D-dimensional, right?
Yeah.
So there are K edges which are dependent
on the remaining edges. Yeah. Mm-hmm.
Yeah. So the projection will be E minus K dimension, right?
Right.
But my question is, is this set of a E minus K dimension lie on a affine space?
Does the E minus?
So they are a subset of a linear or affine space of E dimension.
It's not.
Right?
No, it's not. Absolutely not. It's disconnected, and what I mean, it's okay. Here's what it would look like. Maybe I should draw a picture. So first of all, I think I probably have to explain to people what you're asking. So new share. Okay, so what he's asking is, okay, here's our Euclidean distance cone. This is the best way I know how to draw it. And, as you know, the coordinates of this thing are the are the pairwise distances of the point configuration, of some point configuration. So if we look at these are all the pairwise distance vectors of all possible real point configurations. And so what he's saying is, so these coordinates represent, pairs, really. So, or these are elements of your, entries of your matrix. Those are the coordinates here. And the entries are, as you know, edges of a graph. So if you give me a graph, I have a sort of coordinate subspace. And what he's doing is he's taking and if you remember, the D stratum of this cone, it corresponds to all the point configurations that live in, so P1 through Pn, where each Pi lives in Rd. So the image of all of those under the distance map, that's our D stratum. And what he's saying is, I'm projecting the D stratum on G. So if I take the projection of the D stratum on G, in that previous picture in the slides, I had drawn it. So so he's okay, so the dimension of this thing, this projection, so dimension of the projection on G of the D stratum is exactly, can be shown, and we'll show it, that this is the rank of G in the generic rigidity matroid. Okay, so rank of G in the D-dimensional generic rigidity matroid. So that's going to be the dimension of this projection. And and he called G, let E be the set of edges, and let's say, and you have seen in Tony's class, essentially you have rows of them, some set of E, the edges of E determine the rows of the rigidity matrix. And let's just say this is the generic rigidity matrix. So these are indeterminates. So, and he's saying that, if the rank of G is going to be the number of independent rows. So if there was, let's say, K rows that were dependent, then the dimension of this projection is going to be whatever E is minus K. So E minus K is this rank, right? So now he's asking, what does it look like? What does this projection look like, right? So the projection is typically, I mean, it has the right dimension. It's got a certain dimension. And if it happens to be independent, so if K is 0, there are no dependent edges. If K is 0, then this will be full dimensional. So it will be size of E. So if there are E, so the coordinate subspace has E coordinates. And so this is full dimensional. So it's using up the full dimension of this coordinate subspace. However, it's far from convex, not convex. It'll have all kinds of gaps and stuff in it. And it's definitely not, you know, I don't know, it's definitely not a single affine subspace or anything like that. Okay, so this is a pretty ugly object. The only thing we know is that it's got little neighborhoods that have the full dimension. If it had been independent, if it is not independent, then this won't have the full dimension. It'll only have dimension E minus K. Okay.
Meera, is it a semi-algebraic set, the projection?
Yes, because the projection is all the possible distances for edge lengths for the edges in B dimensions. Right? Yeah, so that's, you know, you can define that using your Cayley-Menger equalities and inequalities, and yes, it's a semi-algebraic set.
Okay, thanks. This picture is really helpful for me too.
Okay.
Okay, yeah. So basically, you cannot find an affine space of E minus K dimension that contains this this set, right? You cannot.
That contains it. Yes, of course, the entire coordinate subspace contains it.
Yeah, but I mean a subspace of E minus K dimension.
Of that dimension. No, often.
No, yeah. But they are
You mean if
they are connected.
K is not equal to 0. If K is equal to 0, then the entire coordinate subspace contains it.
Yeah. If K is not 0, then you
Yeah.
cannot. Okay. But they are connected. But it's connected, right?
It's connected because it always contains 0.
So that means
The project
if you move
from the origin, you can make all the edges 0. So you can go from anywhere to anywhere through the origin. But of course, if you take, typically what they look at is, you know, instead of looking at the entire cone, you sort of look at the slice of the cone given by the sum of the edges equals 1 or something like that, you know. Then it won't be connected. Not necessarily connected.
sorry, it's a slice of what?
Yeah, that's a good question, actually. So, so basically, often people, they don't look at the entire, if you look at the entire cone, it's connected, right? So you can go always to the origin and back. Any D stratum is connected. Maybe I'm answering a question you didn't ask.
And projection is also connected, right?
Yes, projection is also connected. Yeah.
That means if you move one, you can
go from
traverse the whole-
anywhere to anywhere in a continuous path. Yes.
But if you
move continuous
the origin,
yeah, the E minus K parameters, right?
You can always go to the origin. Yeah.
Yeah.
but if you remove the origin, if you just remove the 0 matrix, it's not connected.
Upstairs, it's still connected. Downstairs, it may not be.
Oh, okay. That's interesting.
Yeah. So,
Okay.
well, actually, well, let's talk about that later. It's confusing to me. I have to think about it.
Mm-hmm.
Okay. It's certainly not convex. That's for sure. Even with the origin.
Is there an easy way to see why it's not convex?
For some graphs it is, and those graphs are called the deflattenable graphs. But because for those graphs, what you can show, here's what you can show. you can show that if there's a graph for which the projection of the D stratum is convex, then in fact, it's the projection of the whole thing, the entire cone. So the projection of the D stratum coincides with the projection of the entire cone. So what that means is it says that whenever there is a Euclidean realization of this graph in any dimension, it always has a Euclidean realization in D dimensions.
That's really interesting.
Yeah. Okay, so this is probably the first topic we will do. I haven't decided how I want to order the different, I mean, we finished the tour of topics and I'm going to go, and we've given some of the basic theorems and proved some of the basic theorem. And now I want to go more into a little more detail into each one of the topics separately. That doesn't mean that they're going to be completely disconnected from the rest. I'm still going to sort of point out connections. But I have not decided what order to do this in, especially because I don't know, has Tony, it'll be good for if you guys in the rigidity class have finished, things about the D-dimensional rigidity matroid and all that stuff, so that I can talk about these projections and other things about that. So maybe what I first do is solving polynomial systems that arise from these distance equations, and maybe generalize it a little bit to other constraints besides distance constraints. And we talk about that first before we go here and talk about projections of the cone and things like that. I haven't decided what order I'm going to do the details in.